Transverse waves, the particles oscillate perpendicular to the direction in which energy is transferred, meaning they move up and down while the wave travels horizontally. This is clearly shown by the rope vibration, where the hand moves the rope up and down, creating peaks called crests and valleys called troughs along the rope. This pattern of movement is typical for all electromagnetic waves, such as light and radio waves, as well as mechanical waves on a string. The key point is that the motion of the particles is at a right angle to the energy flow, which distinguishes transverse waves from other types of waves. Longitudinal waves transfer energy through vibrations that move parallel to the direction of energy flow, as shown by the compression and expansion of coils in this example. The coils vibrate back and forth along the same direction that the energy travels, creating regions where particles are compressed together and others where they are spread apart, which we call compression and rarefaction. A common example of this type of wave is a sound wave, where air particles oscillate parallel to the wave's movement to carry sound from one place to another. This back and forth pattern of particle motion is what distinguishes longitudinal waves from other types, like transverse waves. Here, we can see the difference between oscillation and propagation in waves more clearly. The key point is that while the wave itself moves forward in one direction, the particles within the medium move differently depending on the type of wave. In longitudinal waves, like sound waves, particles oscillate back and forth parallel to the direction the wave is traveling. This creates compressions and rarefactions as the wave moves. On the other hand, transverse waves, like those on a string or light waves, cause particles to move perpendicular to the wave's direction. The particles move up and down while the wave moves forward. This visualization helps us understand that wave propagation is the travel of energy through the medium, while oscillation is the movement of particles around their fixed positions within that medium. Waves can be classified based on the medium they need to travel through. Mechanical waves require a medium, like a solid, liquid, or gas, to move from one place to another. This means they can't travel through empty space, because they need particles in the medium to transfer their energy. On the other hand, electromagnetic waves do not require any medium at all. They can travel through a vacuum, like the space between the Earth and the Sun, without needing air or any other material. This difference is important because it determines where and how each type of wave can propagate. Waves are classified in two main ways: by how their particles oscillate and by whether they need a medium to travel through. When we look at the direction of oscillation, transverse waves move particles perpendicular to the wave's direction, like light or a wave on a rope, while longitudinal waves have particles vibrating parallel to the wave's flow, like sound. Another way to classify waves is by their medium requirement. Mechanical waves need a medium, like air, water, or a solid, to propagate. Examples include sound and water waves. On the other hand, electromagnetic waves don't need any medium and can travel through space, such as light and X-rays. So understanding these two categories helps us see the full picture of how waves behave in different contexts.